Alright, welcome to this lecture video. This is the Chapter 5 Probabilities section. We are only going to be doing the first 4 sections from Chapter 5. There are many other sections in Chapter 5, but we are not going to be covering them. And so we are going to focus in on sections 5.1 through 5.4. And the learning objectives here for 5.1 is kind of a lot going on. We're going to understand the random processes and the law of large numbers, apply the rules of probabilities, compute and interpret probabilities. We'll be doing that using the empirical method and also the classical method. And the fifth objective is to recognize and interpret subjective probabilities. All right. So this is really just an intro to probabilities. Let's look at the first objective a little closer. So random is basically unpredictable result or outcome and probability. And here, simulation's another definition. It is a technique used to recreate a random event. Simulations can be tactile or virtual. In both instances, the goal of the simulation is to measure how often a certain outcome, such as getting ahead in a coin flip, is observed. So oftentimes we will simulate a random event by flipping a coin, and we try to figure out what's happening there. So to see this idea, suppose we flip a coin 100 times and compute the proportion of heads observed after each toss of the coin. So the first flip is tails, so the proportion of heads is already 0 out of 1. The second flip is heads, so now the proportion is 1 out of 2. So on and so forth. And we continue on like this, and then finally, after the 100 flips, we'll plot the proportion of heads versus the number of flips that we've obtained. So in figure A, we repeat this experiment with the results shown in figure B to see this idea. Figure A and B both illustrate a random process. So let's take a look at these probabilities here. So here's a proportion of heads. Notice that by the 100th flip, the proportion of heads is very, very close to 0.5. The experiment was repeated, and the two graphs are very different. However, by the 100th flip, the proportion of heads is spot on. Okay? So it's a little messy, but eventually the proportion of heads will converge onto that 0.5 amount. Alright, so here we say a random process presents scenarios where the outcome of any particular trial of an experiment is unknown, but the proportion or particular outcome is observed approaches a specific value as the number of trials increases. Alright, so we're going to get into some probability here. It says basically the definition of probability, it is a measure of the likelihood of a random phenomenon or chance behavior occurring. So we have to quantify randomness and probability. It is a branch of mathematics. It is a part of statistics. We're going to be using the idea of probability to make inferences about our results. And that's going to allow us to make very accurate predictions, and we can also measure our certainty on how likely our predictions will be true or will hold true. Um, so here it says probability deals with experiments that yield random short-term results or outcomes yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. So here's the law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. All right. And we saw that in the example. As we repeated flipping a coin, the proportion of getting a heads got closer and closer to the real probability of that outcome. And we know the probability of getting a heads is 1 out of 2 or 1/2. The law of large numbers is often interpreted as a non-existent law called the law of averages by folks who misunderstand the law of large numbers. Yeah, sometimes we call it the law of average, but I guess more precise is the law of large numbers. In probability, an experiment is any process with uncertain results that can be repeated. The sample space, called S, of a probability experiment is the collection of all possible outcomes. An event is a collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. We will denote events with one outcome, sometimes called sample outcomes. Called simple events. In general, events are denoted using a capital letters such as E. A probability experiment consists of rolling a single fair die. A. Identify the outcomes of the probability experiment. And so here's the situation. Rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6. These are the different little events. And there's 6 different results. Determine the sample space. The set of all possible outcomes forms the sample space. There are 6 outcomes in the sample space. Define the event E equals roll an even number. All right. So the event E, roll an even number, will have 2, 4, and 6. So that is the sample space. A fair die is one in which each possible outcome is equally likely. For example, rolling a 2 is just as likely as rolling a 5. We contrast this with a loaded die, in which a certain outcome is more likely. For example, if rolling a 1 is more likely than rolling a 2, 3, 4, 5, or 6, the die is loaded. All right, let's look on to the next objective. Apply the rules of probability. So the first thing you need to understand about probability is that the probability of some event must be greater than or equal to 0 and less than or equal to 1. So it's inclusive. It can be 0 or 1. The probability ranges from 0 to 1. The sum of the probabilities of all outcomes must equal 1. So that is, if the sample space is E1, E2, so on and so forth, n times, then the probability of each little one, the summations of all those probabilities, will add up to 1. It is certain to occur. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probabilities. So here we have this, it's basically a probability distribution table here. The color of plain M&M milk chocolate candies can be brown, yellow, red, blue, orange, or green. Suppose a candy is randomly selected from a bag. Table 1 shows each color and the probability of drawing that color. And so the colors, these are the different colors, that would be our sample space. And the probabilities of each one is between 0 and 1. We also have to verify that the summations of each event will total 1. And if we were to add them all up, we do get 1. If an event is impossible, the probability of the event is 0. If the event is a certainty, probability of the event is 1. An unusual event is an event that has a low probability of occurring. So here in Objective 3, we'll compute and interpret probabilities using the empirical method. So approximating probabilities using the empirical approach. The probability of an event E is approximately the number of times event E has observed, divided by the number of repetitions of the experiment. So the probability of E is roughly equal to the relative frequency of E. So there's basically two definitions of probability. It's the frequency of E divided by the number of trials of experiment. So we'll do an example. It says an insurance agent currently insures 182 teenage drivers. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on these results, the probability that a teenager will file a claim on his or her auto policy in a given year is 24 out of 182. And this is roughly 0.132, and that's what we got. So this is like the empirical probability. So for every 100 insured teenage drivers, we expect about 13 to have a claim on their auto policy based on this. All right, so that's that ratio, or the proportion 0.132 is 13%. So that is per 100 there, 13 per 100. Okay, here's another scenario. It says the data in Table 2 represent the results of a survey in which 200 people were asked their means of travel to work. Use the survey data to build a probability model for means of travel to work. Estimate the probability that a randomly selected individual carpools to work. Interpret this result. Would it be unusual to randomly select an individual who walks to work? So now we've calculated the probabilities. There were 200 people. We've divided them. And now we see what's happening. So we can now answer certain questions based on the probability of certain individuals carpooling and things of that sort. Here's the probability that an individual walks to work. That's approximately 0.025. So if we were about 2.5 people per 100, or you could just round it to a nice whole number, 25 out of 1,000 will walk. Now it's time to compute and interpret probabilities using the classical method. So here's the classical method of computing probabilities requires equally likely outcomes. An experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. Computing probability using the classical method. So here it is. If an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is n, then the probability of E is the number of ways E can occur divided by the number of possible outcomes. So if S is the sample space of this experiment, where NE is the number of outcomes and E and NS is the number of outcomes in the sample space, we get that ratio. And so now we can look at some examples here. It says a pair of fair dice is rolled for die or die where each outcome is equally likely. Fair die are die where each outcome is equally likely. And we're always going to be talking about fair dice. A. Compute the probability of rolling a 7. And you have a pair of dice. You need to compute the probability of rolling a 7. Compute the probability of rolling snake eyes. That is, compute the probability of rolling a 2. And the only way to get a 2 is by getting 1 and 1. Comment on the likelihood of rolling a 7 versus rolling a 2. So here is basically the complete sample space of a pair of dice. There are 36 possible outcomes. We got 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, all the way down 6 by 6, 36 different possibilities. Now, how many of them have 7? How many of them have the snake eyes? Well, that is the snake eyes. It's just going to be one outcome out of all of this. Now, rolling a 7, though, okay. There's different, we have to figure out our sample space. Well, the sample space is actually 36, but we need to figure out how many have a combination of 7. And here we list it out. 1, 6, 5, 2, 4, 3, another 4, 3, 5, 2, 6, 1. So it's that diagonal. And there appears to be 6 different outcomes where you can actually get a 6. And that's out of 36. So we'll say the probability will be 6 over 36, which reduces to 1/6. You have a 1/6 chance of getting a 7. That's pretty good, actually. How about the outcome of rolling snake eyes, which is 1 out of 1? Well, that's 1 out of 36. Okay, and then finally, let's compare rolling a 7 versus rolling a 2. And as you can see, the probability is 6 over 36 versus 1 over 36. That's rolling a 7 is 6 times bigger, 6 times more likely. And here's another way to explain it. In 36 rolls of dice, we expect to observe about 6 sevens and only 1 2. So that's a big difference between them. So here's another scenario. And here there's Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. To be fair, Sophia randomly selects the 2 people who can go with her. So Sophia's going to take a ticket, and then she's going to only select 2 people. Determine the sample space of the experiment. In other words, list all possible simple random samples of size n equals 2. Compute the probability of the event Michael and Kevin attend the concert. Compute the probability of the event Marissa attends the concert. Interpret the probability in part C. Alright, so we do need to list out the sample space so we can see all the different combinations. Alright, now it says here we have for part B n equals 6, s equals 6, n of s equals 6, and there was only one way the event Michael and Kevin attend the concert. So out of all the different 6 possibilities, the sample space, only one of them will have Michael and Kevin. Okay, so we can actually calculate that probability. It was 1 out of 6. Now the other event was Marissa attends, so she's going to be paired with someone else. It doesn't matter who. We just want to know how likely is it that Marissa will attend. Well, we do need to go back to the sample space. It looks like Marissa is in 3 different groups out of the 6. So Marissa has a 1/2 probability, 50% chance of being selected. And if the experiment was conducted 1,000 times, about 500 of those times, Marissa would be attending the concert. Here's another scenario. Okay. Suppose that a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. Estimate the probability of having 2 boys and 1 girl in a 3rd child family using the empirical method. Compute and interpret the probability of having 2 boys and 1 girl in a 3rd child family using the classical method, assuming boys and girls are equally likely. Alright, so using the empirical probability of this event, 2 boys and 1 girl happening, we know that based on the data that we were given, 180 and then 500 families, and we're assuming everything is random and having the child was random, we get a 36 chance. Alright, so that is about 36 per 100 families. The probability that a family is having a family of 3 children will have 2 boys and 1 girl is approximately 0.36. What about the other case? Alright, so one way to do the empirical, or the other probability here, would be to create a tree diagram where we list out all of the different possibilities. And now out of the full sample space of 3 children, these are all the different possibilities. You can have boy, 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 girl, so on and so forth. How many times does 2 boys and a girl come out in that sample space? As you can see, it's 1, 2, 3, 3 out of 2, 4, 6, 8. So the 3/8 probability there. And we get 0.375. And now you would interpret it. Let's look at the last objective here. It is recognize and interpret subjective probabilities. So subjective probabilities of an outcome is a probability obtained on the basis of personal judgment. For example, in economics, uh, predicting there is a 20% chance of recession next year would be a subjective probability. So 5.2, the additional rule and complements. So use the addition rule for disjoint events. So two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. So we often draw pictures and Venn diagrams to represent different events. Here you see let E represent the event of choosing a number less than or equal to 2, and let F represent the event of choosing a number greater than or equal to 8. These events are disjoint. Alright, so the probability of E happening is 3 out of 10. Probability of F happening is 2 out of 10. The probability of E or F, right, you'd be a total of 5 over 10. That is the sum of those two. So here's the addition rule for disjoint events. Basically, if E and F are disjoint events, then the probability of E or F is the sum of the probability of E and the probability of F. It can be extended for more than just 2 events. This rule holds for many, many different events that are all disjointed. Here's another case. Here is our addition rule at play here. So it says in 1881, Simon discovered that digits do not occur with equal frequency. The physicist Frank discovered the same result in 1938 after studying lots and lots of data. He assigned probabilities of occurrence for each of the first digits as shown in Table 5. The probability model is now known as Benford's law and plays a major role in identifying fraudulent data on tax returns and accounting books. Verify that Benford's law is a probability model. And so one thing we need to check is that the values are between 0 and 1, and the sum of all of them totals 1. Determine the probability that a randomly selected first digit is 1 or 2. Well, we're just going to add up those two since they're all disjointed. And we get 0.477, and we can interpret this to mean about 48 out of 100 would begin with 1 or 2. So here it says use Benford's law to determine the probability that a randomly selected first digit is at least 6. Now, at least meaning 6 or more. So this is really just the probability of 6 or 7 or 8 or 9, and you would total those probabilities, and this is what that would mean. So it's a 0.22% chance of getting a first digit of at least 6. So here's a standard deck of cards. Now normally we do not use decks of cards in practice just because a lot of people are not familiar with decks of cards. So you can't expect this type of example to be on a midterm or a quiz. It's good to work on it in homework though. Compute the probability of drawing a king. Well, there's 52 cards, there's 4 kings. Probability will be 113. Compute the probability of the event E drawing a king, or F drawing a queen, or drawing a jack. So here it is. A standard deck of cards has 4 kings, 4 queens, and 4 jacks. These are all exclusive. And so here it is. The probability of king or a queen or a jack is just going to total 3/13. So here's the second objective. And this time they're not going to be mutually exclusive. So we're going to look at this example here where there's an overlap. And when you have to calculate the probability of an overlap, you cannot overcount the 1/3 since it belongs to both sets. You don't want to count it twice. It only needs to be counted once. So we have to be very careful in how we proceed. All right. So it's this little piece inside needs to be subtracted out eventually. So we're going to look at that. So in general, all right, that for any two events E and F, this formula holds. The probability of E or F is equal to probability of E plus the probability of F minus any overlap. Now, if they're mutually exclusive, this overlap is 0. Now, here is a case of 52 standard deck of cards. Suppose a single card is selected from a standard deck. Compute the probability of the event E drawing a king or drawing a diamond. Now, there are 4 kings. There are 13 diamonds. However, there is 1 diamond that's a king, or 1 king of diamonds. And so we wouldn't want to double count the king of diamonds in our calculations of this probability. All right. So what we need to do is calculate the probability of kings, probability of diamonds, and then subtract out the probability of the king of diamonds, that one card that is both a king and a diamond, so that we do not double count that card. And this is how it works, and that is the probability for 13ths. So table 6 is called a two-way table because it relates to categories of data. The row variable is the marital status. Each row describes the marital status, and the column variable is gender. So each box inside the table is called a cell, right? Now here's some questions. It says determine the probability that a randomly selected U.S. resident is 15 years old or older. Determine the probability that a randomly selected U.S. resident 15 years older or older is widowed. Determine the probability that a randomly selected U.S. resident 15 years old or older is widowed or divorced. And then determine the probability that a randomly selected U.S. resident 15 years old or older is male or widowed. Now let's go back to this table here. And I'm assuming that this represents all of the individuals that are 15 years old or older. They didn't say, but I guess we can assume that that's what the data means. First, add up all of the columns. For example, the males, we add them all up. And we get 126.9. And then we add up all of the never married column, 86.1. Then you add the row totals there. You add all the rows and you total it all up. You get 126.9 divided by 260. All right. There are 150, here's question B, the answer to B. There are 15.2 million U.S. residents 15 years old or older who are widowed, and therefore the probability would be 15.2 divided by the total. The events widowed and divorced are disjoint. We use the addition rule to calculate that probability. So the probability of widowed or divorced, and that's the answer. Okay, probability of male or widowed. All right, well, there is an overlap, so we do have to subtract out the male or widowed column there. All right. What about the complement of an event? Sometimes we call it e to the c power there, or not c power, but 1 minus pe. That's the complement. So here is an example of the complement. So it says, according to the Gambling Commission, 52% of Americans have played the state lotteries. What is the probability that a randomly selected American has not played a state lottery? So it would be the opposite. They are complements of each other. So we'd simply just subtract that probability from 1. The two probabilities, the complements and the events, must total 1. So here we have income distribution of households in the United States in 2017. Compute the probability that a randomly selected household earned the following incomes in 2017. Here is the other case, less than 200,000. So one way to compute less than 200,000 is to calculate 200,000 or more and then take the complement of that. So you would subtract that. So that was a pretty clever way to calculate that. So at least 10,000, and so that phrase at least, the phrase at least means greater than or equal to. The complement of at least 10,000 is less than 10,000. So in 2017, 7,804,000 households earned less than 10,000. So the probability of random selecting a household that earned at least 10,000, therefore, is this. So we can take the complement of the less than 10,000 there. Another clever way to calculate the probabilities. Let's look at 5.3. This time it's independence and the multiplication rule. So it's a little different from being disjointed and non-disjointed. And also it's different because we are not adding up the probabilities. In this case, we'll be multiplying probabilities. Right? So first you do need to be able to understand and identify independent events, and then use the multiplication rule for independent events, and then also compute at least probabilities. So two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. So two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So suppose you flip a coin and roll a die. The events obtain a head and roll a 5 are independent because the results of the coin flip do not affect the results of the die toss. Are the events earned a bachelor's degree and earn more than $100,000 per year independent? No, because knowing that an individual has a bachelor's degree affects the likelihood that the individual is earning more than $100,000 per year. Two 24-year-old male drivers who live in the United States are randomly selected. The events male 1 gets in a car accident during the year and male 2 gets in a car accident during the year are independent because the males were randomly selected. This means what happens with one of the drivers has nothing to do with what happens to the other driver. So here it says disjoint events versus independent events. Disjoint events and independent events are different concepts. Recall that two events are disjoint if they have no outcomes in common. That is, if knowing that one of the events occurs, we know the other event did not occur. Independence means that one event occurring does not affect the probability of the other event occurring. Therefore, knowing that two events are disjoint means that the events are not independent. All right, so they're trying to really get you to understand the difference between disjoint events and independent events. They're just two different concepts, right? Let's look at the multiplication rule for independent events. So here is the first formula we have. If E and F are independent events, then the probability of E and F is equal to the probability of E times the probability of F. So in the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 21 2 times in a row? Well, the first thing we got to think about is this an independent event? And yes, it is. Rolling and spinning the roulette wheel and having the ball circulate around before it drops in, they're independent of each other. Well, it turns out that there are actually 38 different possibilities, 1 through 36, and then 0, and then 00. And so there's only one of those that have 21. So there's during the first roll, you get 1 out of 38. Now, when you spin it again to get 21 on spin 2, it's going to be another 1 out of 38. And what we need to do is multiply those two probabilities up. 1 over 38 times 1 over 38. And we actually get 1 over 1,444. This occurring is a very low chance. It's very rare for something like this to happen. It's, I mean, the percentage is even, you know, very, very minute. It is a very rare occurrence, okay? It's unlikely to happen. Let's look at this rule for n number of independent events. They're all independent, therefore we would simply multiply the probabilities together to calculate the probability of all those events in conjunction of each other happening. Here's an example. Here it says the probability that a randomly selected 24-year-old male will survive the year is 0.9986 according to the National Vital Statistics Report. What is the probability that 3 randomly selected 24-year-old males will survive the year? Well, and we're assuming they're all independent of each other. The probability of all 3 males survive will be this. We multiply, and it's still going to be pretty high. All right. What is the probability that 20 randomly selected 24-year-olds will survive the year? Still pretty great chance, okay. 0.9724. All right, let's look at compute at least probabilities here. So it says compute the probability that at least one male out of 1,000 aged 24 years will die during the course of the year if the probability that a randomly selected 24-year-old male survives the year is 0.9986. So at least one out of the 1,000. All right. At least one will die. That's a tricky question because they give us, let's go back here for a second. They give us the probability that one survives is 0.9986. So here's the formula that we'll use. The probability of at least one dies is the complement of none dies. It's at least one. So we can really just do 1 minus the probability that none will die. And and here we have it again. We have 1 minus the probability that first survives, second survives, so on and so forth. That's a lot. All those probabilities, I mean, it's 1 minus 0.9986 to the, well, they have the 20th power. That I don't believe that would be the 20th power. I believe that would be the 1,000th power. And we're getting 0.2464. Let's double check this on our calculator here. Let's do 0.9986 to the 20th power. No, they actually mean 0.996 to the 1,000th power. Yeah. And then 1 minus that last answer there. Alright, so it's just a little typo. It means 1,000 there, okay? And so here's some rules just to kind of summarize the probability rules. Probability must be between 0 and 1 inclusively. The sum of the probabilities of all outcomes of the sample space must total 1. And if E and F are disjointed events, then the probabilities of E or F would be the sum of the probabilities of E and F. If E represents any event and EC represents the complement, then the probability of the complement is 1 minus PE. And we also have if E and F are independent events, then the probability of E and F will equal the probability of E times the probability of F. Notice that OR probabilities use the addition rule, whereas AND probabilities use multiplication. All right, so the word OR kind of implies addition and AND implies multiplication. .4 Conditional probability and the general multiplication rule will be explored in this particular section. Let's dive in. Compute conditional probability. So we do have a different notation. This is the probability of F given E, and it's read as the probability of event F given the event E. It is the probability that the event F occurs given that event E has occurred. So it says, suppose a single die is rolled. What is the probability that the die comes up 3? Now suppose that the die is rolled a second time, but we are told the outcome will be an odd number. What is the probability that the die comes up 3 again? Well, the first roll, the sample space was 1, 2, 3, 4, 5, and 6. It's probability 1 over 6. And the second roll, they said that it was 1, 3, 5. And we also know that this is 3 given the outcome is odd. The probability is therefore 1/3. Notice that the conditional probability reduces the size of the sample space under consideration. So if we limit our sample space, we have 3 different values. The outcome is odd, and then it's just 1/3 out of all 3, so 1/3. So if E and F are any 2 events, then the probability of F given E will be equal to the probability of E and F divided by the probability of E happening. Alright, so we can do this using data from a two-way table. Compute the probability that a randomly selected individual has never married, given the individual is male. So since we're given that the individual is male, we know that it is out of the total number of never married, and then given that they're male. So that restricts the total. It's not the total of all of the people in question, it's just the total given that they were male. So let's look at this. We're getting the probability of 46 over 126.9. Let's look at how this works. The total number of males and the fact that there was only 46 that were never married. The probability, therefore, is 46 out of 126. Compute the probability that a randomly selected individual is male, given the individual has never married. Alright. So this time the given never married is the restricted total column, and then it's out of the number of males who've never married. Alright, pretty straightforward, pretty straightforward. Here's another example. Again, suppose that 12.7% of all births are preterm. The gestation period of the pregnancy is less than 37 weeks. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? Is this unusual? Well, we simply go through the probabilities that were given. It was restricted to being preterm, so that is the total amount. And we also was given that we have 0.0022 as the probability of weighing 8 pounds, 13 ounces. So our final answer is about 1% of those babies, okay? Out of 100, almost 2 will be that much. It is considered unusual. Any value less than 5%, or 5 out of 100 chance, is considered unusual. Compute probabilities using the general multiplication rule. So here is that general multiplication rule. The probability that two events E and F both occur is the probability of E and F is equal to the probability of E times the probability F given E. So here's an example. It says the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? So we have the probability of a driver who is speeding and gets a ticket would be E and F put together, and we would have to multiply these two probabilities. We would get 0.72. Here is another situation. It says, suppose that 100 circuits sent to a manufacturing plant. Out of those 100, 5 are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What is the probability that the plant manager discovers at least one defective circuit and rejects the shipment? Alright, here we go. So we're actually going to construct a tree diagram for this. And then we will add up those probabilities. Remember, at least one defective is not none are defective. There's another approach. We can do it this way. And then finally we have this. If 2 individuals from this group are randomly selected, what is the probability that both choose themselves as their favorite other? Notice that the second one is 42. Let's go back. 42 over 1519, and then times 42 over 1519. That's for part C, but for part B we have it reduced by 1 each time. Alright, so if small random samples are taken from large populations without replacement, it is reasonable to assume independence of the events. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. And then finally, two events E and F are independent if the probability of E given F, or equivalently, if the probability of F given E is equal to the probability of F. All right. All right, let's take a look at some of the practice problems, and we'll just jump into 5.1 here. Let's just kind of screen some of those questions and see what kind of questions are there. Yeah, this is a very interesting question. It says, suppose you toss a coin 100 times and get 95 heads and 5 tails. Based on these results, what is the probability that the next flip results in a tail? I would say 5 out of 100 chance. I'll round that to 0.05. Yeah, based on those results. All right, let's look at this data set here. All right, so the data is filled out, but they want us to divide each one by 585, and then we get our probability distribution. Yeah, we can answer those questions. Not too bad. All right, let's look at 5.2. Yeah, these look like some pretty good questions here. They're mutually exclusive, so we simply will just add them up, and that should be the answer there. Not too bad. Determine whether E and F are independent of each other. A person having an at-fault accident and then the same person being prone to road rage. Interesting, interesting. Yeah. There seems to be some sort of connection between these events. Um, so I'm not convinced that they're completely independent of each other. I mean, that's, so just go through that. That's pretty straightforward. Nothing too tricky there. Let's go back here. Pretty straightforward here. Alright, so here we have the probability that a randomly selected 4-year-old male feral cat will live to be 5 years old is 0.98528. What is the probability that 2 randomly selected 4-year-old fetal cats will live to be? So we'll do 0.98528 times 0.95828. Let's see. 98528. And then we're getting 0.97078. Let's see if it accepts that. And it does. Let's take a look at 5.4. Suppose E and F are two events, and the probability of E and F is 0.1, and the probability of 0.5 is there. Well, what is the probability of F and E? Okay. Yeah, so this is just a matter of using that formula that we looked at. And once you plug those into the formula, you should be good there. This is a similar question, but this time it's the probability of E and F. So we would just multiply these two, so I would get 0.4. Let's check it. It's good. Alright, might help to create a two-way table. Let's look at the data here. Alright. Yeah, it's not too bad looking. Probably can open it up and create the sums of the tables and things of that sort. Okay, so there is a question using the 52 standard deck. Hopefully you're all familiar with that. Shouldn't be a problem. Let me know if that becomes a problem, and we can change that around a little bit. These problems will be good for you to study. So we'll leave these problems as is. And if you're having any problems with the homework, reach out to me and I'll make a helpful video going over the problem in more detail. Look at, view an example. Look up some resources online, also inside of Stat Lab, and the YouTube videos and links that we've posted as well. Take care.